already and it was abnormally long, so I'm going to try to not do that this time. So, rate laws basically are a part of chemical kinetics that measure the speed of a chemical reaction. It's basically how fast or slow it goes, and the components that determine how fast or slow this reaction goes. Think about it, if you have a really large pot of boiling water and a small pot of boiling water, the smaller pot is going to boil a lot faster because it's a lot less of H2O that needs to boil than the bigger pot. Excuse me. So that's kind of like basically what rate laws measure, just how fast or slow a chemical reaction wants to go. When you I'll just do this. When you figure out rate laws, you're going to have a normal chemical reaction written out like this, and you are only, so this side, reactants, which you should probably already know, this is the products of the chemical equation. And with rate laws, you do not care about the products. You only are using the reactants to calculate your rate laws. And so, there's kind of like one standard formula for rate laws, which is rate equals K, concentration of element A to whatever power it's raised to, concentration of the element to whatever power it raised to. And we will get into what all these mean because it kind of look a little confusing. So K in the equation is the rate constant. And it just kind of determines the speed of the chemical reaction. It's not the rate itself. It's just a constant, value that determines the speed. That's a component that helps determine the speed. X and Y, these little guys right there, I'm going to use a different color. These little guys right there are exponents that determine the element order of the rate, which is basically the speed of how each specific element is moving of the reactants. And when you add those two little guys, you get the overall reaction order. And I'll show you how to do that in a second. Which determines the overall speed of the whole entire reaction, not just element A or element B. Which we'll get more into that in a second. And then the concentration of elements is the molarity of each component in the rate reaction. Which is just how concentrated it is, Cool. So, an example for this, if you need a little understanding, because sometimes it's going to be a little confusing, is when you're using that powdered lemonade or Kool-Aid to make your drink, if you're going to add more of your Kool-Aid powder to your water, the more you add, it's going to be more concentrated. So the more atoms or moles that are in an element or compound, the more concentrated it is. Cool. So that you can't even see that, And that's not even part of what we're doing right now. Oh my gosh. Here. There we go. So, as I was saying, I'll show you a little bit more about the exponent and the orders. So, let's say you have element A in your rate law equation, and it's raised to the second power. And you have element B, and it's raised to the first power. You know that element A is in the second order, since it has raised to the second power. You know element B is raised to the first order. And again, it's not really too complicated. It's just kind of the speed that they're going at separately. But then you add these together for the overall reaction order, and you get 3. Because 2 plus 1 equals 3. which is third order. So then you know the reaction is at third order. So that might be a test question where she gives you something like that and is like, what's the overall reaction order of the reaction? You just add the exponents together and you figure out the order. They do go up to like 4th, 5th, 6th order, but I didn't even learn about that, so the highest you're ever going to see is 3, which is pretty nice. And then, really quick, before I end this video, because I don't want to make them too long, just kind of your basics, which would help you, with everything, is writing your rate laws. So I have a few really simple examples that I learned. So here we have a chemical reaction where O3 is decomposing into O2 and just regular oxygen molecules. And when you want to write a rate law, like I said, you totally forget about the products. They don't even matter. And you only focus on the reactants. I'll leave it in red. So, like I said, your basic formula for this is going to be rate equals K times the molarity or concentration of your reactant, which is here is O3. And since there's only one O3 molecule in this whole equation, you know it's going to be first order because it's raised to the first power. So that's how you kind of calculate the orders of each element when looking at an equation. You kind of like transcribe it. The amount, that's not what I want to do. The amount of each element is then going to go and be your order exponent, which I hope makes sense. So another example I have to make things a little more complicated is you have two NOCl compounds. NO2Cl, my bad. And it decomposes into two NO2 compounds and some chloride. Again, don't care about these at all. This is the only thing you need to solve writing out your rate law. So it's rate equals K NO2Cl, concentration of that. And like I said, since there's two of these, you know it's going to be to second power, which means second order. So like I said, this is very basic rate law stuff, so I wouldn't be surprised if she gave you some equations kind of like this and was write a rate law, or if it's multiple choice, pick the right rate law, and just always remember that it's only the reactant side and that the amount of molecules determines the order.